Hi, I'm John Zuleger, President and CEO of Integrated Power Services, and I welcome you to episode 3 of the Respond, Rethink, Resolve podcast. And today I'm joined by Stuart Cheek, who's our division president for the electromechanical division. Welcome to the podcast, Stuart.
Thank you. Great to be here.
I always like talking to you. You know things I don't. And one of them is you really know a lot about electric motors because before you came to IPS, you worked for a manufacturer of electric motors. So
Right.
I'm really looking forward to exploring today some of the things you learned about how the manufacturer of electric motors have changed over the last 20 to 30 years. And we're definitely going to explore the implications of that for the end users who bought those motors and are now going to operate those motors for the next several decades.
Good.
And then we're also going to explore some real macro themes around reshoring and electrification and what the implications of those events are going to have on the age of our manufacturing infrastructure in North America. So, Stuart, let's get started. You had built this career at Reliance Electric, which was a branded, well-known electric motor manufacturer, and eventually got acquired by ABB, and it's still an active brand among the ABB, electric motor brand family. In doing that, you were involved in design for manufacture. Maybe you were lightly involved in the actual design, but you had to build these motors in factories. And so you've had a unique insight as to what changed with materials, what changed with components, what changed with just with overall design and operability of these motors. So when you look at what you learned, over the course of that 25, 30 years, let's get into some of the things you saw happen with electric motors.
Okay. Yeah, I mean, I'll speak to more of the large horsepower motors that we repair. Typically, go through a repair process. But one of the interesting things that I saw happen over the years was when I first got into the industry, almost all large motors were designed to purpose, right? Mm-hmm. So, I mean, it was a painful process for the customer. They had to wait for the design, they had to wait for the manufacturer and all that. But the great thing about this—
Can I just interrupt? What kind of purposes? What were some of the top 2 or 3 purposes that drove motor design?
Yeah, like oil and gas, for pumping applications. There was, rolling mills or mining duty motors, that sort of thing. You had AC, DC, all kind of different technologies too. But over time, and when I first got into that industry, there was a real small segment they called general purpose. And, those were easy motors, right? You put them on the shelf. They were designed to a NEMA specification. So over time, that segment continued to grow and grow and grow because it was easier, it was less expensive, and honestly, it allowed offshore manufacturers to compete in the U.S. So by the time I left the industry on the OEM side, fully 50% of large motors sold were now in this segment. So you think about a general purpose motor that, electrically and mechanically isn't designed to fit exactly anything. It's really designed for an average application. And, that changed the industry significantly because now, just in the example of contamination, when you were designing to purpose a motor for that application, you build it with certain enclosure integrity to protect the motor against contamination. Well, now a general purpose motor isn't designed like that. So, the contamination would get into the motor and it would shorten the life of the motor. So that was one aspect of what I saw, really happen in the market. The other thing really is, and the game with cost reduction. I mean, there was a real push to reduce costs and make machines lighter and take active material out. And the best, way to do that is to put more power in a smaller frame size. So, that makes the whole motor, run hotter because you're taking active material out, pushing the active material remaining.
Active material is
that's a good
for
question.
example?
So copper and E-steel, which is magnetic grade quality steel. So when you take that out of the design and push those materials harder to achieve the power, it just, it translates to more heat. And heat is the big enemy of an electric motor.
So in other words, same or smaller size, same power,
right,
less raw material, lower cost.
Right. That's exactly right. What we used to say is, you can only put as much power in as you can get heat out. Mm-hmm. So, the cooling schemes were highly engineered, and but the effect of that is the insulation materials had to withstand more heat, which shortens the insulation life of the motor. So that was two things that I saw, happen definitely over my time in
this aspect of the heat. They run hotter. Give us some idea of how much hotter.
Well, I mean, if you look at a motor that was manufactured, 20 years ago, the nameplate would have a certain temperature rise. So let's say, it's 1,000 horsepower at 80-degree rise. A motor today may be 1,000 horsepower at 100-degree rise. So that's the normal operating temperature of that motor when it's running at that rating.
At 100, so it'll increase in heat by 100?
Right.
Okay.
Runs 20 degrees hotter to get the same power.
And so when we talk about the degradation ability of heat, what happens? Take us kind of inside a motor when it's subjected to that higher heat. How does the failure start to occur?
Yeah, that's a good question. Two things. If most heat-related failures are either the insulation system itself. So every part of the insulation system, whether it's the mylar, the resin, the tapes that protect the copper going outside of the copper, all of those are designed to operate at a certain temperature. You go above that and it degrades a lot quicker. So, every degree that you run that motor hotter reduces the years of insulation life that motor has. And on the mechanical side, most of the time you'll see that in reduced bearing life. So you may have to re-grease that motor more often because the grease is getting too hot and it shortens the life of that bearing. Well, not everybody maintains their motors like that. Mm-hmm. So the bearing will fail and create the failure of the motor.
As I entered this industry, because I had really no understanding or familiarity with electric motors 13 years ago, obviously learned a lot, right? And one of the things that I find interesting here in 2026 is that you really don't know exactly how much remaining life is left on a motor, right? Yeah. So why is that so? And what does that mean for an operator and an end user as they're making operating decisions and deciding, am I going to if I don't know how much life is left,
right,
I don't know how much time I have, right?
Right. And, in critical applications, that's why you have spares, right? You just so you can, rotate that failing motor out and put your spare in. But one of the things that we would see is that, as a motor goes through its life, in our service shops, we may see that motor, 5-10 times to recondition it. And after 5 times of reconditioning it has to be rewound, mm-hmm. right? Mm-hmm. So that means the insulation life is exhausted.
The layers have run thin.
Right.
And you're about to go to ground.
You're about to go to ground. Yeah. So a well-designed machine can go through a rewind process 3, 4, 5 times. So you think about a 20-year life cycle, multiple reconditions where you're just replacing bearings, cleaning everything up, then a rewind, now multiple, reconditions and another rewind. So through 20 years, we may see that motor, 15, 20 times.
So when we think about an electric motor that's in operation and has to stay running, I'm always fascinated with the fact that we really don't have a great way of measuring how much remaining life is left in that motor. And I know because I've talked to reliability engineers and operating unit engineers that they have to make this risk-based decision in a moment in time. And it's like, first of all, they're encouraged to keep running and make more product and not take downtime. But on the other hand, they risk a catastrophic failure on a motor that could lead to downtime. And if it's really catastrophic, expensive downtime and damages. So when you look at just an operating motor that's in an operations and it can't be shut down, what kind of measurements can you take to estimate the remaining life on an asset like that while it's running?
That's a good question. I mean, there's two types of testing that generally goes ongoing, and one of those is vibration testing. You'll see, you've got a good baseline when the motor is new of how that motor is operating from a vibration standpoint. And over time, as the motor ages in the bearings or it's picking up contamination internally, you'll see the vibration levels escalate. And the other one is temperature rise. Again, you start with a baseline of what that motor is operating. I mentioned an 80-degree rise earlier. If you see that motor increasing in temperature, something is going on, either internal friction or contamination or something. And both of those things are, real strong indicators that you've got a failure going to happen right around the corner.
So, Stuart, sticking with design changes, we talked about what you call the active components, the copper and the key components to the insulation system. What about some of the more passive components of a motor? What has changed over time with those?
Yeah, I mean, every pound that you can take out of a motor, it reduces the cost for the manufacturer. So, with all the advanced design tools, finite analyses, you can optimize the thickness of castings and take a lot of weight out of them, or sheet metal. So, OEMs have done that. And honestly, that a thinner casting allows the motor to cool more efficiently too. So there's some advantages to going to smaller, thinner castings. But that's really what they've done. But you'll see a lot of failures now often occur on the mechanical components too. You'll have, cracks in feet or fans that fracture prematurely just because, the vibration has increased beyond what that mechanical component can stand.
Yeah.
So it'll fail.
So to your earlier point, motors aren't designed and built the way they used to. And I've been in some of our shops and I've seen 100-year-old motors that we repair and go right back into operation. I mean, those were tanks back in the day, right? And so they're not built that way anymore.
Right.
So what are the implications? Do you think repair life cycle intervals are getting shorter because of these design cost out changes?
I absolutely do. I mean, the manufacturers may say it's still designed for a 20-year life. The problem is that 20-year life is probably going to come at an expense to the user to maintain it a whole lot, more formally than that tank that would have been, in that location previously. So, if you want to get to a 20-year life, you're having to invest in more lubrication intervals, more pulling the motor to be reconditioned, and that sort of thing. So the cost of ownership is higher, or the life will be shorter, one or the other. One of the things we hear a lot about is reshoring manufacturing in the United States. And from most standpoints, we see that as a positive for our economy and national security and all those things. But that's driven by trade policy, tariffs, supply chain risk. What does that mean for the electromechanical infrastructure that has to support it? And how ready do you think it is?
Yeah, I really want to take a moment and share where I saw this happening. I remember in 1988, NAFTA was passed, and I got into this argument with my brother, who was a union worker in a paper mill. And the argument was, I think this is going to be great for us. And he's like, this is going to destroy us. And this was like, a weekend of ongoing debate on whether NAFTA was going to be good, for the U.S. manufacturing base or not. I thought it would lead to more customers and a strengthening of it. But the reality now is that was passed in 1988.
So he was right.
He was right. I've admitted to him. He was right. He's smarter than me in so many other ways. And so when you really look at what happened, if we're just going to click on the North American manufacturing base, that includes Canada as well, same forces and factors, is certainly manufacturing left the base. And it moved to maquiladoras in Mexico, and definitely moved to China and Asia and a variety of other low labor cost environments. And so over time, on episode 1 of this podcast, Hannah Kaplan and I really unpacked the impact that had on power generation, load demand. And there was a time when the manufacturing base was 18% of the GDP of the United States. Yeah. And now I believe it's like 11%, right? So that was a major demand of electricity customer. And that's another way you can see how it just depleted and went away. Mm-hmm. The demand for electricity went away, and so did motors go away, right? With that environment. And so what I think the impact has been is that the manufacturing base that stayed, it wasn't like it wasn't invested in, but it hasn't been maintained at the same level, right? So you have this long-standing, multi-decade drain and outsourcing of the manufacturing base in North America with the beginning of NAFTA. So infrastructure sitting there, and it's been through a lot of trade wars. It's been through a lot of, global competition impacts. Mm-hmm. And there's just been a bunch of delays and pauses in investing, maintaining, and growing. Now we have some macro thematic things that might start indicating things are going to change. And there's a difference between articles that you read about these things and really seeing it in the real world. And I'm going to come back around to the second part. But I definitely believe we have a combination now of the use of the U.S. National Defense Act in a way that we have not seen in this country since probably World War II, right? So clearly industries like defense, shipbuilding, critical minerals, pharma feedstocks for pharmaceuticals, and certainly chips for computing. These are all industries where the U.S. government has determined we're going to set up policy, we're going to set up financing, and in some cases, we're going to take ownership in companies to make sure this gets reshored. So certainly since 1988, we haven't seen the use of the National Defense Act, at this aggressive level, at least by the U.S. government. Trade. So obviously there's been a recognition of this hollowing out of our manufacturing base. And certainly the current government has taken a much more aggressive protectionist trade approach from a policy standpoint. And so that's led to tariffs, and that's led to a reexamination. And that's coming on the heels of NAFTA, where global supply chains got pretty stretched. I think we all felt like there was no risk, no hazard of having my product begin manufacture on the other side of the planet and then be component assembled somewhere in between and put on a boat and shipped in. We just thought, there's no hazard, there's no risk to such extended supply chains, but COVID really exposed that. It did. Right? And so I think you've got supply chain security issues that are exacerbated by trade. And the effects on all of this has also been inflationary. In the case specifically of electric motors, I think you and I have continued to stack up the data that the price of electric motors new has risen between 20 and 40% just since 2021. So here's the rub. So we've got real beginning evidence that reshoring is not just a newspaper article or an online article. It's actually starting to happen.
Yeah.
There is real investment in capacity expansion and new capacity coming in some of these industries. And what I find interesting, because we've supplied these markets for so long, steel, paper, and others, is when you have some impetus, even data centers, even though there's not a lot of electric motors in use, they're demanding feedstock and components. So there's demand positive effects on steel and paper and chemicals and these other industries that use a lot of electric motors. But I think the concern I have is if that is lifting, and I think it is, it's going to happen against an under-maintained, depleted infrastructure because of decades of not having a policy approach. And then I look at things like Canada, for example. There's absolutely a decoupling of a longstanding positive trade agreement and relationship with Canada that's unraveling to some degree.
Right.
And that's definitely had effect on Canada as well. What will this mean for electric motors? I think electric motors are going to get tested, right? Yeah. Wouldn't you expect it's going to be challenging, and we can't make enough electric motors to replace them all when they fail.
Right.
I mean, would you expect more repair cycle? And
I would for the reasons that we talked about earlier, and the shorter life cycle and higher, cost of maintenance to support them. I would expect that, companies like IPS, the demand is going to increase.
Mm-hmm.
So electrification, we hear a lot about that, is one of the biggest themes in heavy industry right now. What does wider electrification actually mean for the motor and drive infrastructure underneath it? And where is the system most exposed?
Yeah, there's some overlapping themes that we see emerging. First, energy is expensive. It's getting more expensive. I think affordability is impacting not only the consumer, but affordability is impacting all manufacturers, right? Who still are a source of low demand for electricity to drive their processes. So I think, number one, affordability is leading to a lot more interest out of efficiency. So end users are trying to find and seek ways to use less power to drive their processes. And we just talked about how their output and capacity is probably elevating while they're trying to reduce their actual consumption of electricity. Yeah. That's a rub. And against an aged infrastructure. That's going to be a challenge. So if you have, a large installed motor base, I think it's not only with each individual motor, you have challenges with waste inside your processes. And that's in the equipment in between the electric motors. On the front end, the electric balance of plant. Yeah. Those losses, those energy losses, they pay for at the substation level. Yeah. Right? But they get leaked in the protection and control, of what they call the electrical balance of plant, before it hits the motor. Yeah. And so, I really want to talk to you more about, what some strategies are to drive energy efficiency. So going back to these motor designs, are motors more efficient?
They are not less efficient. I mean, we talked about some of the ways that manufacturers have reduced cost and put more power into a smaller frame size to reduce cost. But that really hasn't had a negative impact on efficiency, but it does have some trade-offs with like inrush and other things that you have to take into account for, your protection and control and switchgear and that sort of thing. But there's, the government in the U.S. Endeavored several years ago to increase the efficiency of all electric motors, going back, to 60% of all electricity is consumed by electric motors. So, you have to be concerned, especially in an aging infrastructure, to make that as efficient as you can. So they passed all these, they call it EPACT, and they, offshore manufacturers predominantly were lower in efficiency than those manufactured in the U.S. for technology and other reasons. But, so that through that legislation, they leveled the playing field on efficiency. And it had, it had the right effect, but it also had some unintended consequences on competitiveness across motor manufacturers.
Well, the other, in order to frame the energy efficiency trend that we're seeing, I'm going to ask you to come back to the fundamentals a little bit.
Okay.
So let's say we connect an electrical current to an electric motor. Just take us into that. What happens when electricity is connected to an electric motor?
First of all, I'm a mechanical engineer.
You're an engineer and I'm an economist, so you're better suited than, to answer it. But really, the direct across the lines starting of electric motor induces waste, doesn't it?
It does. We think about, motors being, 90, 92% efficient. And, the rest of that is waste. And it's mostly, heat, thermal type waste. So there's all kinds of, concerns. One of the things that in my 30 plus years in the motor industry, I never saw an application where a motor would not start a load. And what that means is that every engineer that specified a motor oversized that motor so they wouldn't be the first one to, stall out a load. So with that over engineering, you're burning more electricity than what you really need. So that's always been interesting to me. And, engineers are by nature very conservative. So they put a lot of margin in their designs.
So, but when you electrify a multi-phase electric motor, does it automatically start up to its rated revolutions per minute, or does it ramp?
No, it's, I've always said an electric motor is kind of a dumb animal. If you don't put a soft start or some type of delay, mechanism in place, soon as you start it across the line, it's going to get as quick as it possibly can up to speed with, whatever torque's designed into the motor.
That stresses it, and it's violent, and if you do it repeatedly, it reduces its life.
Right.
Because of the violent forces involved. Yeah,
you think about how motors are used in applications like to run a conveyor. If you start a conveyor unloaded, it's one type of event. But if you start that conveyor fully loaded, and something's going to break, right? So they put controlled start gearing or gearboxes or whatever in place to control that.
So with respect to ways end users are trying to access more energy efficiency, along comes the popularity of variable frequency drives. So can you unpack for us what VFDs bring for end customers that are trying to drive more efficiency with energy consumption?
Yeah, VFDs they were a game changer when they came into the market. They were pretty dirty to the motor when they first started designing them because they were real damaging to, because they were varying the frequency of that electrical current. But they've become pretty friendly over time, so they don't damage the motor and shorten its life. But the positives are that, most processes I mentioned, pumps, fans, and compressors are the biggest application for VFDs. And because most of those don't need to run, full speed all the time. So what a drive will do is vary the speed of that motor based on the load requirements of the process. So if you can, slow down a motor and run it at a different frequency, that's energy savings. So that's the VFDs are the best way to make your process more efficiently.
Do you have any just ballpark range? How much more efficient can you make a motor putting a VFD on the front of it?
Well, the energy savings can be up to 30% is kind of the rule of thumb. So it's significant.
Yeah. And a VFD is essentially what? Is it smart?
Yeah, it is. I mean, I would call it the brains that you try to put between the power source and the motor. But here's the interesting part. When you think about pumps, fans, and compressors alone, I mean, it's a big segment of the electric motor applications. But really, so up to 60% of motors can be ran on a drive, but because it hasn't, there's a cost to doing it. So, I mean, really only when I left the industry 5-6 years ago, about 35 to 40% of motors actually run on a drive. So there's a opportunity to, for users to save energy by putting drives on there, and it's usually less than a 1-year payback to do that.
Yeah, so it's very compelling.
Yeah.
I think the final aspect that we're seeing as it relates to the quest for energy efficiency is really automated operating from the advent of sensing and software. Mm-hmm. And so, we definitely have seen, more sensing, come onto the motor designs. When you think about, that's just the individual piece of equipment. When you talk about process industries, sensing has had a huge impact on being able to see the process, manage the process. And we talk a lot about distributed controls. Like, you cannot operate an oil and gas refinery or pulp and paper mill without a distributed control system to take all this sensed equipment and be able to automatically, through control limits, run the process, right? And some of it is closed loop into control limits. So it automatically will change valves and so forth just to make sure, it's all operating at one process. But with respect to energy efficiency, hasn't this had a huge also impact on having just total processes become more energy efficient?
I would say yes. Not only the motor, but all things downstream from the motor are also optimized for energy efficiency.
So, Stuart, as we continue to talk about what we're seeing on our end user customers' quest for energy efficiency, let's talk about continuous monitoring. This aspect of being able to see where waste is occurring and managing it is certainly of interest to all of our end users. And so, when we look at what the purpose of continuous monitoring is, can you break it down for us? Like, how do you go about continuous monitoring? What are the equipment and what do you do with the data? And when it works, what does it look like?
Yeah, I mean, most continuous monitoring systems, it's made up of hardware and software. And it sounds like a great idea. I mean, reliability engineers, that would be a dream of being able to, see how their processes are working when they're not there or it's being run unmanned. And a lot of OEMs have started down that path, thinking that would give them a competitive advantage, and it would up to a point. But what we found is as you get more into concerns around cybersecurity, that's really the only word you have to bring up, and it makes everybody nervous, right? And we've seen some high profile cybersecurity failures that have just cost companies millions of dollars. So it's difficult to convince through a business case for somebody to risk a cybersecurity event for the abstract chance that you might predict a failure that may never occur.
We've definitely seen this at IPS, and I can tell you, over the course of my time here, we commissioned and conducted 2 engineering technology surveys. And because I was concerned on the one hand about this extending repair life cycle as it came in, but I also saw it as an aftermarket opportunity. Is there going to be a solution that we can add on to a repair and bring information and monitoring, to an asset? So we did it twice, these surveys, and both times it kind of came back with this kind of picture. Are there sensors you can add to electric motors? Yes, there are. Right. Are there software that can take that sense data and tell you information about that motor? Absolutely, there are. Can you do that for groups and clusters of motors in a manufacturing environment? Yes, you can. That data has to be collected if it's add-on, either through a Bluetooth or a near field type technology. Yeah. Better be explosion proof. Right. And so have we experimented and piloted? Absolutely we have, but here's what happens. You usually get a very eager, interested reliability engineer who gives you a pilot in the process to experiment with. They get some data, they take it to the unit manager or an operations manager. Oh, that's interesting. It makes its way to the plant manager. And usually that's where it dies. And it dies because they want to expand it. And they bring in corporate IT security and they say, what? You've just put an aftermarket solution on the wrong side of the firewall. Right. And some of these industries have, federal, obligations for cybersecurity, right? So to me, almost anything, and I reserve the right to change my mind about this if the technology evolves and fails. But for now, 13 years on running, you can run all the pilots you want. I don't see these add-on solutions as scalable. And what it really comes down to, I think, then is being behind the firewall. So how does continuous monitoring evolve from here? What do you think has to happen?
Well, I don't know that we will overcome the cybersecurity thing. Again, maybe that does work itself out. But the systems that seem to be, acceptable by all parties is systems that wholly work behind the firewall. And again, though, I mean, if you think about an AI environment where you can trend a lot of data quickly, those trends are important. So there are some value to being able to predict failure, to monitor trends, to drive uptime in your processes. That's probably where it's going to end in, the foreseeable future.
Yeah. Well, the companies that really build and implement and sell distributed control systems, to me, have a natural advantage.
Yeah, I would
think
so.
Are they coming and utilizing it with AI? I think so, but I can't say we've seen, clear and strong evidence that our end user customers are implementing that with any kind of speed or haste. They're probably really expensive, right? Because they're highly engineered, very bespoke solutions, right? Distributed control systems.
Okay. That's a good discussion, John. I think it is certainly relevant. But where does this go? What does a more complete picture of asset health look like, and what has to change to get there?
Well, I think what we're talking about is it's not as if our end customers' whole processes are just 100% filled with electric motors. Certainly what we've discussed is electric motors are critical to most of these processes. Yeah. They take electricity and they create horsepower that drives these processes. So they're absolutely mission critical in that respect. But I think where this does go is the cost of sensing will continue to fall. Right. I do think AI has an ability to manage massive data sets.
Yeah.
I do think the technology already existing can be adapted to take those data sets and on an automated basis, analyze whole complex processes in a way that we can operate them more efficiently. And I also believe these investments will probably lead to automation because we don't have enough skilled workers. Mm-hmm. And so the other aspect of automation that's going to be required for reshoring to continue to occur is to drop the cost of manufacturing to be globally competitive.
Yeah, that's a good point.
Right? So I see a convergence at the end of the day, right? Like there's the potential to hit all the marks of energy efficiency, using AI, lowering the cost of manufacturing, automating to be globally competitive. And I think when that happens, you'll really see, the real wave of reshoring of manufacturing in North America in ways that are really direct and visible. So again, thank you for your insights today on this episode. Isn't it fun to work at a company where we get to see these macro themes and these forces play out? I mean, do you feel that way every day?
Absolutely. I mean, all the industries we touch and products that we get to see, failure modes that we get to help solve, it's a lot of fun.
Yeah. In closing, the thing I hope people who consume this podcast who aren't our employee discover is that ours is a very dynamic industry. Ours is relatively AI safe. If you're going to build a career, you still need your hands and your brains to do this work. It's not repetitive. It's very problem solving and bespoke. Robotics is going to have to go a long way before it's ready to wind a motor, right? And so I think it's a space where someone can come and we aspire to be an employer that we want to employ you for your whole career. That's really aspirational. And are we in a position to do it right now? I have to be honest, we're working toward it, right? It really comes down to the employee value proposition. What does an employee want to get from their employer? What do they expect? And at a basic level, what we know is that employees want to be heard. They want to be understood. They want to be autonomous. They want to be empowered. They want to feel like they're working for an employer that's got a plan for them, that has structure, that can train them. They want to be compensated at a market competitive rate for the accumulation of skills and experience. So this is what we're aspiring to be. And I believe we'll continue to make progress in this area. And it really comes down to, us doing a good job of telling our story on the amazing careers we can enable and build for people.
Agree.
So thank you for your time today.
Thank you. I enjoyed it.